This is number 45, and we're going to explore modeling a population. So the problem says, suppose a population P of rodents satisfies the differential equation given. So initially there are P of 0 equals 2 rodents, and their number is increasing at a rate of dp/dt, which is 1 rodent per month when there are 10 rodents. The question is, how long will it take for this population to grow to 100 rodents, to 1,000, and then in general, what's happening? So every application has given information, right, and a goal. So we have a given and a goal. So what is given? Well, we have some variables here. So we know that, so let's just say P we know is the population. So let P be population of our rodents. And of course, our T here is time, specifically in months. We're given a differential equation. So our differential equation is dp dt equals k and then a capital P squared. Okay, this dp dt, right, this is very important. This means this is the rate of change, right, of the population P. So WRT with respect to, well, with respect to, of course, the time, which we know is T. Okay, so dp/dt means the rate of change of the population as time goes by. Now, this differential equation, there's a lot more in the problem, but I want to go ahead and explain this because you have a couple of problems, 32 through I think 35 in your homework. Now, what this says, so this is saying that the rate of change of our rodent population with respect to time is directly proportional to the square of the population. Okay, so from maybe pre-calculus or even just algebra, you learned about direct variation, or it's something, a quantity is directly proportional to another quantity. So this is saying that the rate of change. So let's go ahead and maybe write it here. So the rate of change of P with respect to time, so let's just write it in words, is proportional, keyword proportional, right? Or another way of saying proportional, varies directly to, let's see, let's fit this in here, the square of the population. So I'll abbreviate that, population. So again, the rate of change with respect to time is directly proportional to the square of the population. So whenever you work with proportionality, right, that means if your independent variable increases, right, if something increases, then the output increases. Well, of course, if the population is increasing, then of course the rate of change, right, I mean, it's going to keep increasing. So hopefully that makes sense. It doesn't always have to be square. It might be the square root. You might not have a square. It really just depends on the model. So this is, again, we're going to keep seeing these problems as we go on. And let's see, so we have an initial condition. What else is given? We have P of 0 equals 2, right? So this is our initial value, right? This is, I mean, really, so P of 0 equals P naught, right? So our 2 is P naught, right? This is our initial value or starting point. So let's see, we're also given and their number is increasing at the rate of dp/dt. Okay, so dp/dt equals 1, right? So this is, right, 1 rodent per month, right? Where, I mean, we're starting at 10. When there are 10 rodents. Okay, so we have a lot of given information here. We have, okay, so we have this guy right here, We also have this initial condition, and we have a rate. Okay, so that's all the given information. So now what is the goal? So again, given, and this is just good practice with communicating mathematics to somebody else. You're telling the reader, myself, what the given information is. After reading the problem, this is what you get. And then now what is the goal of the problem? Well, the goal is, right, how long will it take for the population to grow? So how long will it take, let's see, for this population to grow to 100, right? And then, of course, 1,000, is it 100? Yes, 100 and 1,000 rodents. Okay, and this is a word problem, so I want to see words, especially if you're explaining something, right? I mean, I could just do the math, but this is a word problem, so we have to interpret this. Okay, so let's go ahead and do the problem or finish this up. So, okay, so this is what we have, and we're looking for time. So, I mean, we have some relationships here. We do have dp dt, which gives us kp squared, and we also have another dp dt. So, I mean, we can set these equal to each other, right? Because this is dp dt, this is dp dt. So since, all right, so explaining, since dp dt equals kp squared and dp dt equals 1, then we can definitely say kp squared is equal to 1, right? So we have this relationship. And, I mean, what else do we have? Well, okay, so we've used, let's check some, so I've used that. I've used this rate. And we have kp squared equals 1. Well, we definitely know p is 10 when this happens, when the rate is 1. So we can use that information. So we have 10 times, or k times 10 squared equals 1. Well, this is really 100k equals 1. So k is 100. Okay, so k is 100. And k, again, this is actually called the constant of variation or constant of proportionality. So let's see, okay, what we have. Well, again, the goal is to find how long it takes. So the goal is we have a differential equation here, a very simple one, and we want to find a solution that is a formula that helps us predict this population. So we're looking for a p of t. So let me just make this a little bit bigger. So remember that dp dt, so dp dt, right, that's the same thing as p prime of t, right? Or sometimes the book might say p, just p prime. So we want p of t. We want that unknown function. So there's actually from problem 43, if you look at 43, and you take a look at if you read the problem, there's a nice part A. If k is a constant, which we have, show that the general, so one parameter solution of our differential equation is given by this x of t. And this is exactly what we have. We have so dx dt, so ours is just dp dt, kx squared, well, again, this is just kp squared. And it's given by this differential this solution, our formula. So x of t, so let me go ahead and actually write that down. X of t equals 1 over c minus kt, of course, where c is an arbitrary constant. And in our case, our x is p of t, is equal to, and I'm just going to go ahead and write it as 1 over c minus kt. So this is a solution to our differential equation. And let's go ahead and make this a little bit smaller. And let's see. I think my iPad is losing its battery because I'm trying to zoom in. And, oh, okay, there we go. Okay, so this is what we have. But we know what K is, and we want to find C. So we have, I mean, let's use what we have. Our P of 0 equals 2, right? We haven't used our initial condition. Right, way up here, our P of 0 is 2. So P of, okay, so this is just, okay, P of 0, let's go ahead and write it in 1 over, I'm going to leave C alone because that's what we want to find, minus, well, K is, okay, 1/100th. What's our T? Well, our T in this case is 0, so, I mean, this is all 0, which is very nice, because we just get 1 over C, and P of 0, well, we start with 2 from our initial condition, and then of course if we solve for C, right, C must be a half. Okay, so now we can rewrite our P of T, right, as 1 over, well, what's my C? Well, I have a half minus T 100th. So I have, this is a nice model, a nice formula to predict our rodent population. But we can simplify this, make this look a little bit nicer. I'm going to multiply by 100 because we can. This is a complex fraction, so we get 50 minus t, right? So just using a little bit of algebra to make that look nice. So we have P of t equals 100 over 50 minus t. So this guy, this is a nice particular solution, right? It's a formula that predicts our population as time goes by. And what's the question? Well, the question was how long does it take for the population to grow to 100 rodents? Okay, so 100 rodents, well, if it's 100, then we got to put 100 in there. 100 over 50 minus t. And then, I mean, this is just really algebra. This is not very hard. We can cross multiply. 150 minus t equals 100. I'll go ahead and do dot, dot, dot because this is very easy algebra. And we get t equals 49. Okay, so it takes 49 years, or 49 months in order to get, in order for the population to grow to 100 rodents. Okay, well, what happens if you insert 1,000, right? We want 1,000 rodents. Well, if you, I mean, do the same thing, whoops, right? If you actually insert 1,000 in here, you're going to do the same thing. 1,000 equals all of this. So 1,000 equals this expression. Okay, so I'm just going to go ahead and write my t because this is very easy algebra. When you solve for t, you're actually going to get 49.9. So 49.9 months, so almost 50 years. Now, if you actually graph this, which you really should, you can do it on your graphing calculator, but it's actually it's a rational function. So we have 100 over 50 minus t, so we definitely have an asymptote at, there we go, at t equals 50, and the graph looks something like this. So we have this guy, and we have this guy, right? So that should remind you, I mean, that's a rational function. That's what our P of t looks like. And, I mean, this model is probably, I mean, it's only really accurate from 0 to 50 because, I mean, in real life, the rodent population can't, I mean, go to infinity, right? Resources and predators will and definitely put limits on this growth, but it's still a good model. You know, it does a pretty good job of predicting this. So, I mean, we're really looking at, I mean, this solution here, and it's growing and growing, but I mean, the math says, well, there's going to be infinitely many rodents, but we can't have it because of, environmental constraints. And we're going to see a lot of more of these problems. So here P grows without bound, definitely explodes as T approaches 50. So that is number 45.